This is one of the more challenging theorems to prove in Math 3, and so I'll encourage you to study this video carefully and to make sure before proceeding to each step that you've understood the previous one. Okay, so first I'll read the theorem. The theorem states, points on a perpendicular bisector of a segment are exactly those equidistant from the segment's endpoints. Now, if you're like me, this means almost nothing unless you look at a picture. So let's go to the next slide. Okay, before I even read the theorem again, this is the segment we're talking about, segment AB. You could name it anything you want, but since they're the first two letters of the alphabet, they were pretty handy. Okay, so this is segment AB. This is its perpendicular bisector. It's called that because it's perpendicular to the segment, it forms a 90-degree angle, and also because it bisects the segment, which is to say it cuts it cuts the segment into two congruent segments. Okay, that being said, let's return to the theorem. It says that points on the perpendicular bisector, I've labeled a few points on this perpendicular bisector. They are exactly those points that are equidistant from the endpoints of the segments. So point A and point B. This is actually, it's really saying two different things, and so I've kind of pulled this theorem apart into two different theorems. It's actually a conditional statement and its converse. Both happen to be true. So, and I put it in if-then form so it's easier to prove. The first statement basically says if a point is on the perpendicular bisector, so if you're somewhere on this perpendicular bisector, you're the same distance from A that you are from B. The second part of the theorem, as I've broken it up, is the converse, which is to say if you're the same distance from A and B, then you have to be on this line. So because this is really a two-part theorem, we have to prove both parts, and we're going to do so individually. So first, the first part. If you're on the perpendicular bisector, you're the same distance from A that you are from B. Okay, so we're used to proving things that have a given and what we're supposed to prove. So the given here is that D is on line EK. D is on, I'm going to say it's on the perpendicular bisector of segment AB. Okay, and what we have to prove is that it's the same distance from A that it is from B. So the way to write that would be that DA is the same distance as DB. Okay, we like doing two-column proofs. On the left, I'm going to have my statements. On the right, I'm going to have reasons. The first statement is always whatever is given. Okay, well, where to go from here? Well, think about what we have to prove. We have to prove that DA is the same distance as DB. So it might be helpful to go ahead and draw those line segments. And I hope at this point that you remember doing proofs in geometry before, and you're seeing two congruent triangles. I hope that's what you see. So let's try to prove that those triangles are congruent. Our methods, we can use side, 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 angle, angle, or angle, angle, side. Let's see what information we can collect about these two that is the same. First of all, you'll notice that this is a right angle, and therefore, this has to be a right angle, right? These two angles right here are supplementary. They're a linear pair. And so we know that they're equal to each other. Also, I remind you, so it's a perpendicular bisector, so it's perpendicular. It's also a bisector. Line EK cuts segment AB in half. Each part of that's equal. Okay, so I'm going to make a note of that. I'm going to say that angle ACD is congruent to angle BCD and segment AC is congruent to segment BC. Okay. Well, how do we know those things are true? We know they're true because we know this is a perpendicular bisector, and that's what it means That is the definition of perpendicular bisector. It says that it's perpendicular, and it says that it bisects. Okay, so we've got two pieces of information, and there should be a third really obvious piece of information. The two triangles share segment DC. So I'm going to say that DC is congruent to itself. And hopefully you remember that is because of the reflexive property. It's the reflexive property of congruence. We'll just write REFL. Okay, so we know these three things, and since we know that, we know the two triangles are congruent. Triangle ACD is congruent to triangle BCD. And the reason we know that is because of the side angle side congruence postulate. Okay, and then since we know that these two triangles are congruent to each other, we know that all their corresponding parts are congruent. So that includes the third side of these triangles. I know that segment DA is congruent to segment DB. How do I know that? Because they're corresponding parts. And I know that corresponding parts of congruent triangles are congruent. So we pretty much proved that part of the theorem, the first half. Although, I do need to point out one case. So we picked a D above the segment. I think it's pretty obvious if D were below the line segment, this would also be true. But what would happen if we were, instead of looking at D, we actually looked at point C? We wouldn't have these two congruent triangles in that case. So we kind of need to examine that situation really quickly. So the first case was D's not on the segment. What if D is on the segment? So that is to say, what if this isn't actually point C, it's actually point D? Well, in that case, we know that it's on the perpendicular bisector. Again, so we know that these guys are congruent. So we have to prove it's the same distance. Well, we can look at it and see that AD and DB are congruent. So that's pretty obvious. Okay. Now we have to prove the converse. We have to prove that if point L is the same distance from A it's the same distance from A that it is from B, then it has to be on the perpendicular bisector. Now I intentionally pushed it off to the side because I didn't want to feel like I'm stacking the deck. Okay. So L is the same distance from those two. Well, it's going to be helpful if we go ahead and draw those two, LA and LB. And in this case, the only thing that's given is that they are equal to each other. Okay? So our given information is that LA and LB are congruent. And what we have to prove is L is on the perpendicular bisector of segment AB. Okay, we need a little more in our picture before we go proving something like that. First of all, we should probably draw that line, or what we imagine will be that line. So it's going to go up past this. All right, I've drawn it in such a way, hopefully you can see that I've got two triangles here. They do not look congruent because I drew L off to the side, I admit that. But hopefully we can prove they are congruent, actually. Okay. I should probably label this point, we'll call it M, because M comes after L. All right, and now columns, statements, reasons, statements are true. The first one's true because it's given. You know that LA and LB are congruent. Now, I want to point out something. What line is this that I've just drawn? I'm going to choose to make it the angle bisector. Okay, if this is an angle, and angle L is certainly an angle, it has a bisector. I just split it down the middle. Okay, and because I made it an angle bisector, I know these two angles are congruent to each other. Okay, so I'm going to add in here that segment LM bisects angle ALB. Okay, so it cuts that in half. So that's in our given as well. I need to jot down here that angle ALM is congruent to, hopefully you guys know, it's going to be congruent to BLM. And that's because the definition of an angle bisector. So we split that in half. Okay, now hopefully you're thinking about trying to show these triangles are congruent. I've got congruent sides, congruent angle, and just like last time, I've got the very obvious segment in the middle that they share. LM is congruent to angle LM, or segment LM, and the reason is again the reflexive property. Okay, so let's keep moving forward. I can prove these two triangles are congruent. Let's do that. Triangle ALM on the left side is congruent to triangle BLM on the right side. And the reason in this case is, again, side angle side. Okay, now we need to stop for a second and think about what we're actually doing here. What do we need to prove? What we want to prove is that line LM is the perpendicular bisector of segment AB. Well, if it's the bisector, that means it cuts it in half. I need to know that AM and BM are equal to each other. I can prove that quite easily. AM is congruent to, well, let's think about this. AM corresponds with BM, so they have to be congruent. The reason is because corresponding parts of congruent triangles are congruent. So I've shown that these guys are congruent. So it's a bisector. We know it's a bisector. Now we need to show that it's perpendicular. So we need to talk about the angles here. Okay? Because these are congruent triangles, I think you'll agree that angle M on the right side has to be congruent to M on the left. I'm just going to squeeze this in right here. Angle AML has to be congruent to angle BML. So, I know they're congruent to each other. Do they form right angles? Well, let's see. I'm going to skip a lot of steps here. I'm going to be honest with you. I need to prove that these are both 90. What do they add up to? They add up to 180, you say? And they're both equal, you say? Well, then they each have to be 90. So I'm just going to write angle BML is a right angle. And how do I know that? Well, I explained why. I'm just not going to write it all down. It was the talking that I did. Okay, so we know that this is a right angle. I'm going to come in with a different color and show that. It's a right angle, and these two parts congruent. Well, it appears that line LM is perpendicular to the segment, and it cuts it in half. So it has to be LM is a perpendicular bisector of AB. And the reason, that's just what it means to be a perpendicular bisector. Okay, and we're practically done. Again, we need to consider a second case. What if L isn't actually on the line segment? Well, in this case, it's very simple. Again, if I know it's equidistant from A and B, then it has to be the midpoint. And so it's going to be on the perpendicular bisector. That's pretty simple. Okay, so really quickly, just to recap what we've proved. We proved that if you're a point on this line, you're the same distance from B and A. Likewise, or after that, we proved just the opposite, that if you're the same distance from A and B, then you have to be on the line. So we proved the theorem.